Hey, hello ib2 students. Welcome my next video lesson, which is related still about chapter 8 energy production. Last lesson we were talking about radiation, about power emitted by black body, and about power radiated by objects of different emissivities, about intensity of radiation. So let's do short revision of this. So in general, power radiated is constant times emissivity times surface area of the object times its absolute temperature to the power of 4. Okay, so what is emissivity? Emissivity is the number from 0 up to 1, which says what is the difference between the real object and the black body. Black body has an emissivity of 1, which means that this is perfect emitter or perfect absorber. Okay, when object has emissivity less than 1, so it differs from the black body. If emissivity is closer to 0, then difference is much more bigger. Okay, so intensity of radiation is power which is emitted by 1 square meter of area, so we can use the same equation to write emissivity, of course, except A. To write intensity, of course, except A. It's constant times emissivity times temperature to the power of 4. Of course, for black body, emissivity is equal to 1. What does it mean? That power emitted by black body is equal to constant times area times temperature to the power of 4, or intensity of black body is constant times temperature to the power of 4. So in each case, power depends on the fourth power of temperature. And we've calculated power emitted by the sun. Do you remember? By using this equation, we've calculated power emitted by the sun. And as I remember, power emitted by the sun was 3.9 times 10 to the power of 26 of watts, which means that in each second the sun emits 3.9 times 10 to the power of 26 joules of energy. Okay? We're also talking about how intensity of radiation depends on the wavelength. Yeah? For black body, this curve looks like this, which means that there is one specific wavelength. The symbol or the index is max, but this is not maximum intensity. This is not maximum wavelength. This is a wavelength for which intensity is the maximum possible. So for this wavelength, the intensity emitted is maximum possible, and position of this lambda depends also on the temperature, because if object is hotter, yeah, for hot objects, I'm going to use, let's say, a blue, this curve lies higher and maximum is the left. For cold objects, I'm going to use red. This peak is located to the right, and it is of course much more smaller. And position of this lambda maximum can be also calculated, because we know that temperature in kelvins multiplied times lambda max is also constant. Okay, this relation is given in your data booklet. Here, this constant is 2.9 times 10 to the power of minus 3. Metrokelvins, so kelvins times meter. It's better to write Kelvin times meter than meter times Kelvin, because meter times Kelvin looks like a millikelvin, which is not true. Okay, so practically we were talking about two relations, about power radiated by the object, which is Stefan Boltzmann constant, times emissivity times surface area of the object times temperature to the power of 4, and about relation between temperature and the lambda wavelength for which is the intensity is maximum, which says that temperature times this lambda is equal to 2.9 times 10 to the power of minus 3, which is constant. Okay? We also analyze this graph, because I remember that I presented also graph of two different intensities, but for the same lambda. What does it mean? If we have two different intensities for the same lambda, it means that temperature of the object must be the same. Look on this equation. If lambda is the same and this is constant, then temperature must be the same. Okay? If temperature is the same, then intensity, which is emitted, yes, depends only on the emissivity, on this, because this is Stefan Boltzmann constant. So if we have the same lambda but different intensities, it means that these objects have different emissivities. If higher intensity, then bigger emissivity is obvious. So we did also this example last lesson. Okay, today let's continue this topic. I'm going to talk about three things: about solar constant, about albedo, and about thermal equilibrium or energy balance. And by using this knowledge, we will try to calculate the average temperature of the Earth, of course by using this simple model of radiation and assumption that the Earth behaves as a black body. Okay? So prepare to the lesson. I hope you have notebooks, you have pens, pencils, you have your powerful calculators, and today some colors, okay, and ruler, because graph plotting. Okay, so let's continue last lesson. You don't need to write a new topic, but the new point is a solar constant. Okay. So let's focus on intensity of radiation. Last lesson we were talking about intensity of radiation, and I told you that intensity is power received by 1 square meter of area, and intensity is measured in watts per square meter. Okay? So let's imagine that you have a point source which emits radiation in all directions. Okay? So it emits a radiation or energy in the form of radiation in all directions. Let's imagine that at specific distance from this object you want to receive this radiation. So you, let's say, places something like a sail, yes, which has the radius, which has an area of 1 square meter. So this is 3D, so it represents the surface 1 meter per 1 meter. Okay? I'm going to create longer lines, it will be more visible, I hope. Yeah. And yeah, don't copy yet, I tell you when. Okay, so let's imagine that this distance is equal to r. Okay, and this area is equal to 1 square meter. So let's name this A. Okay, and now let's move from our source of power P. Let's move further from this to distance of 2r. So let's imagine that now we are located at distance of 2r. So this distance, this is 2r. Okay. So let's look. The same amount of radiation, the same stream of radiation, which is here in this kind of cone or pyramid, yes, covers larger area, because at this distance of 2r, yeah, this area which takes the same amount of radiation is 4 times bigger. Okay, I hope it's visible. You see, this rectangle has an area of 4a. You can imagine a pyramid, yes, of the same angle in the vertex, but of height which is 2 times bigger. Okay, then the side of the base is 2 times longer, which means that area of the base is 4 times bigger. So what is important here? That the same amount of radiation, okay, here at closer distance, yeah, passes through much more smaller area than here at further distance. Okay, so basically, if we are 2 times further from the source of radiation, then amount of radiation which is received by the same area is 4 times less. This relation is known as an inverse square law of radiation. An inverse square law of radiation can be written that intensity at a given distance from the source is power emitted by the source divided by, you can imagine a kind of sphere around the source which absorbs this radiation, so divided by area of this sphere, because intensity is power received by 1 squared meter. So if all radiation illuminates the inner part of this sphere, okay, then amount of radiation which is absorbed by 1 squared meter is total divided by number of squared meters on the sphere, so divided by surface area of the sphere, so divided by 4 pi r squared. So this relation that intensity is inversely proportional to squared distance is known as inverse square law of radiation, which says that if we are further from the source, then intensity is reduced by the factor of squared of the distance. Or basically, if intensity here is I, then intensity here is a quarter of I. Why? Because the area which takes the same amount of radiation is 4 times less. Is it clear? Okay, stop video for a moment and copy this, and when you'll be ready, we'll go forward. Okay, I hope that you are ready. So now, what is a solar constant? Solar constant is something like intensity of sun's radiation above Earth's atmosphere. Okay, so this is amount of solar radiation which can be absorbed by 1 squared meter of the surface area which is exposed to the sun's radiation above Earth's atmosphere. Okay, so it's not influenced by existence of the atmosphere, it's above Earth's atmosphere. So we can use exactly the same equation. So maybe write this. You have this in your Tsokos on page number 332. Okay? Intensity of solar radiation at the top of the Earth's atmosphere. So write solar constant is intensity of, like in your Tsokos, the solar radiation okay, at the top of the Earth's atmosphere. Okay, so this is solar constant. And now let's calculate solar constant. To calculate solar constant, we have to know the average distance between the Sun and the Earth. Okay, it's like it's not given in your data booklet, but I know that this distance is around 150 million of kilometers. So in numerator, SP, you have to take power of the Sun, which was calculated by you in our last lesson. And in denominator, we have to take 4 pi multiplied by average distance between Earth and Sun, which is 150 million of kilometers. So 150 is 1.5 times 10 to the power of million is 6, so 150 million is 8, and kilometers, so 3 more zeros, so 11. So average distance between Earth and Sun is 1.5 times 10 to the power of 11 to the power of 2, of course. Yes? Okay. Use your powerful calculator and calculate this. I'm going to use my calculator, my phone. Okay. So use calculator and calculate this. I have 3.9 divided by 4 divided by pi divided by 1.5 and divided by 1.5 and zeros, and I have 1380. 1380, and the unit is watts per square meter. What does it mean? It means that each 1 square meter of surface area which is located at the position of the Earth and exposed to the sun's directed to the sun, and if it's not influenced by Earth's atmosphere, each 1 square meter receives around 1,400 watts of power, so 1,400 joules of energy per second. This is something which sun gives us a lot. 1 square meter, around 1.4 kilowatts. Oh, let's look. Your typical electric kettle has a power of 2 kilowatts. So 1 square meter is almost enough to power 1 electric kettle, which is, in general, an energy consuming device. Okay, so stop video, copy this. This is solar constant. You must know what the solar constant is. You must know how to calculate solar constant, but fortunately, solar constant is given in your data booklet somewhere. In the constants? Yes, in the constants, yes. Is 1.36 times 10 to the power of 3 watts per square meter. A little bit different result because probably distance between Earth and Sun is a little bit different. Okay, so I'm going to use in my further calculations around 1.4 times 10 to the power of 3 watts per square meter. Okay, stop video, copy this. When you will be ready, we will move forward. Okay, next point, write albedo. Okay, what the albedo is, you have also the same topic in your SOCOS, yes? So albedo tells us what is a ratio between scattered power and incident power. So let's look. If you have an object, it can be atmosphere, it can be a real object, it can be a water, doesn't matter, yes? So if a radiation falls on this object, so write this intensity, which is incoming, incident, in, okay? Then always part of the radiation is scattered and the rest is absorbed. Okay, and albedo, which has a symbol of alpha, is fraction between this scattered and this incoming. Of course, if you have object of given area, you can write albedo in form of power, so power which is scattered, to power which is incoming, not only to intensity. So practically, albedo is a number between 0 and 1. If albedo is equal to 0, it means that all radiation is absorbed and nothing is scattered. If albedo is equal to 1, it means that we have perfect reflector, that all radiation is reflected and nothing is absorbed. Okay? Usually, albedo is a number between 0 and 1. Okay? And what is important in this topic? In this topic, you have to know that average, here you have in SOCOS different albedo. For snow, it's 0.85, okay? Which means that snow is quite a good reflector, okay? Here, charcoal has albedo of 0.04, which means that charcoal takes or absorbs almost all radiation falling on it. Is it clear? In the case of Earth, average annual Earth's albedo is around 0.3. You must remember this number, okay, because it will be used in our further calculations. Okay, so average annual Earth's albedo is 0.3, which means that around 30% of radiation is scattered, reflected by the atmosphere and by the land. Okay, 70% is absorbed. Is it clear? Please stop video, copy this slide, and next slide, our big and long final, we'll try to calculate amount of we'll try to calculate the temperature of the Earth by using simple energy and temperature balance model. Okay? So next slide. Intensity absorbed by the Earth. Okay, remember that term intensity refers to 1 square meter. Is power per 1 square meter. Okay, so intensity absorbed by the Earth means intensity which is absorbed by each 1 square meter of the Earth's surface in average. Okay, how to find this? Let's look. We know that solar constant, S, solar constant, is around 1.38 or 36 in your node. In your data booklet you have 1.36 times 10 to the power of 3 watts per square meter. We calculated this, yes? Do you remember? Previously we've calculated this. Okay, and we know that average Earth's albedo is equal to 0.3, which means that 30% of radiation is scattered, reflected, and only 70% is absorbed. Okay, and moreover, it's very important. Let's look. Sun. If sun illuminates the Earth, only one part of the Earth is exposed to the sun. Second part is at night. Yes, and moreover, only one place on the Earth is exposed directly to the sun at a given time. The rest places makes a kind of angle. I'm talking about the fact that what is visible if we are looking on the Earth. If we are looking on the Earth from the sun's perspective, we see what? We see not sphere, but a kind of a circle, or moreover. Let's look. Okay, this is our Earth, three-dimensional shape, yes? Three-dimensional, yes, Earth is not flat. Okay, this is our Earth. And let's imagine that sun is to the left. So sun's radiation travels from left to right. Okay, part of this radiation travels through the Earth, like here and here. So radiation which is in the cylinder, okay, travels through the Earth. So let's look, but from the perspective of sun, this radiation goes through the circle, yes, of area of the circle which has the same radius as the radius of the Earth. I hope it's visible. So what I'm talking about? I'm talking about the fact that sun's radiation is absorbed only by the circle of radius of the Earth. So let's look. Let's write area which absorbs. AA is pi radius of the Earth squared. Okay, but Earth or this radiation which is captured by this circle is distributed on whole Earth. What does it mean? That this radiation must be enough to cover radiation of the circle. So let's write C, not circle, sphere. So let's write S. Okay, sphere of the Earth, which is area of the sphere is 4 pi radius of the Earth squared. What does it mean? It means that in average only quarter, yes, the fourth part of this radiation illuminates each 1 square meter of the Earth. Again, area which is illuminated by sun is pi r squared. Area which uses this radiation, so whole area of the Earth, is 4 pi r squared. This is area of the circle. So in average, each 1 square meter of the Earth takes quarter of this radiation. Is it clear? So what is intensity absorbed by the Earth's surface? Intensity absorbed is equal to quarter of 70% of solar constant. Okay? Or I'm going to write this in a little bit better way. It is a quarter. Quarter means this, times part which is absorbed. Absorbed means not reflected. So we have to eliminate albedo. Of solar constant, so something which sun delivers to us. Okay? So again, intensity of radiation which is absorbed by the Earth is 1/4 of 1 minus 0.3, because 70% is absorbed, 30% is reflected, of 1.36 times 10 to the power of 3. This is something which sun delivers to us. If you calculate this, the result will be around 245 watts. Okay, let me calculate. 0.7 times quarter times 1.36 times 1000. Okay, due to this data, it's around 240 watts per square meter. Okay, what does it mean? It means that each 1 square meter of the Earth, in average, annually, receives 240 watts per square meter. Of course, at a given time, there are places which receive nothing, like at night, and places which receive almost all exposed to the sun at noon. Yes? So we have, for these places, we have to eliminate only albedo. But in average, annually, each 1 square meter of the Earth receives 240 watts of power. So 240 joules of energy per second from the sun. Okay, please stop video for a moment, copy this, and next part, energy balance. Okay, energy balance. What does energy balance mean? It means that amount of radiation which is absorbed by the Earth must be equal to amount of radiation which is emitted by the Earth. Okay? In average, I'm not talking about the greenhouse effect, global warming, and other factors. In average, temperature of the Earth is constant. So something which is delivered by the sun is used by the Earth and radiated in the space. So in general, energy balance means that Earth absorbs the same amount of radiation as is emitted by the Earth. Okay, so this intensity absorbed was calculated previously, and it was 240 watts per square meter. Okay, and what is intensity emitted? Intensity emitted is Stefan-Boltzmann constant times emissivity times temperature to the power of 4. Okay, so let's imagine that Earth behaves as a black body. To simplify this model, I'm going to use a black body model where emissivity is equal to 1. So we have 240 is equal Stefan-Boltzmann constant, which is in your data booklet somewhere here, 5.67 times 10 to the power of minus 8, times emissivity, I assume that emissivity is equal to 1, times temperature of the Earth to the power of 4. Okay? Calculate this by using your calculators, and I'm going to use the result from Tsokos. Tsokos calculated also, and he obtained a result of 256 kelvins. Oh, okay. Based on this data, but he used 245 as the intensity of absorbed. I have 240. Okay, so use your calculator and check it. I'm going to use the same answer as in Tsokos, 256 kelvins. Okay, so let's look. Due to this simple model, we've calculated temperature of the Earth. The real temperature of the Earth is a little bit bigger. It's around 288 kelvins, so around 30 kelvins bigger. But let's look, we didn't take into account a greenhouse effect. Temperature on the moon, average temperature on the moon is in almost the same distance from the sun as Earth from the sun. So temperature average on the moon is around 30 kelvins bigger than average temperature, 30 kelvins less than average temperature on the Earth, because moon has no atmosphere. So almost the same as 256 Kelvin. So let's look. The idea is that we've used a very simple model of radiation and assumption that both Earth and Sun both behave as a black body, and we've obtained temperature which is very close to the real one. And remember, real one is affected by greenhouse effect. We'll be talking about greenhouse effect next lesson. So it's amazing that this simple model with very high precision, this simple model with very high precision describes or the very high precision gives us temperature which is almost the same as real one. Is it clear? Okay, so let's conclude this. Okay, so let's look. What did we do? We first calculated power emitted by the sun. Okay, power emitted by the sun is Stefan-Boltzmann constant, emissivity, which is equal to 1 times surface area of the sun times temperature of the sun. We've assumed that temperature of the sun is 5800 kelvins. So surface area of the sun was also given. I gave you radius, and we've used Stefan-Boltzmann constant and emissivity equal to 1, and obtained that power emitted by the sun is 3.9 times 10 to the power of 26 of watts. Okay, then we've used power emitted by the sun and radius, distance between Earth and Sun, and we've calculated solar constant. Okay, solar constant was power of the sun divided by 4 pi r squared, when r is distance between Sun and Earth, and we've obtained result around 1400 watts per square meter. Okay, in next step we've calculated intensity absorbed by each intensity absorbed by the Earth by using this quarter. The origin of this quarter is the ratio between surface area of the sphere and surface area of the circle. We've used albedo, which for the Earth is 0.3, and this solar constant, and we've obtained around 240 watts per square meter. And finally, we've used equation that intensity absorbed is exactly the same as intensity emitted. We've assumed that Earth emits the same amount of radiation as a black body of the same temperature, and we've obtained temperature of the Earth as around 256 kelvins. Yes? Okay, you must know way how to do this. Your task now is to calculate it again, starting from the beginning, from power of the sun, at the end for average temperature of the Earth. And so additional homework, you have to read in SOCOS a greenhouse effect. It's page 335. Up to 337. Okay, read this. And the next lesson, we'll start next lesson with simple calculations related with something we did today, plus new topic, probably the last one in this chapter, greenhouse effect. Okay, I hope you like this movie. If you have some suggestions, comments, please write as a comment or write an email to me. And remember, this is your homework. See you next time. Thank you for watching. Good luck and stay at home. Bye.